Hello and welcome. In this video, we're going to be taking a look at the notes for Thermodynamics AP Physics 2. Please remember to pause or rewind the video as needed. Let's begin. Section 9.1, Structure of Matter. If a piece of paper is soaked in rubbing alcohol, the alcohol disappears over time. Explain what the alcohol molecules when the alcohol disappears. Use experiment 9.1 in your explanation. Now, of course, experiment table 9.1 is found in our college physics e-textbook by Edkina. We find that the results of this experiment show that the alcohol and other liquids are composed of smaller molecules. The smaller molecules are constantly in motion and bump into each other. This causes them to spread out and ultimately disappear from the paper. Explain Brownian motion. Brownian motion is a phenomenon that describes the constant movement of particles, like water. Gases, liquids, and solids are all made up of particles, atoms, or molecules. What is the chief difference between the behavior of molecules in a gas versus the molecules in a liquid or solid? In solids and liquids, the molecules are more closely packed, while in gases, the particles are more loosely packed and farther apart. The book defines the ideal gas model in a box on page 322 of the college physics textbook by Edkina. Fill in the blanks of the definition column, then explain what it means in the explanation column. The explanations are given in the paragraph above the ideal gas model box. Now, an ideal gas is basically a simplified gas. So let's begin with our definitions. A model of a system in which gases are considered point-like are because they are small and simplified. And only interact with each other and the walls of their containers through collisions by only interacting with each other and the walls of the container, they do not attract each other at a certain distance. This model also assumes that the particles and their interactions are accurately described using Newton's laws. The collisions described obey Newton's third law specifically, with action-reaction pairs. And finally, all collisions that our particles undergo are elastic collisions. Elastic collisions conserve momentum and kinetic energy. It assumes no loss in energy in the form of heat transferred to the environment. Section 9.2, Pressure, Density, and the Mass of Particles. Explain what the particles of a gas are doing that cause the pressure on a surface. As air particles move randomly, they eventually collide with the solid surfaces of the object in the container. Each of the collisions, the particle exerts an impulsive force on the walls of the container, and force exerted on an area is pressure. Look at the experiment table 9.2 in the college textbook in Edkina. Explain what the particles of gas are doing that make the balloon partially inflate when there is air in the jar. When there is air in the jar, the collisions of the particles happen more frequently. This results in increased pressure outside the balloon and the balloon only remains partially inflated. When the balloon fully inflated, when there is no air in the jar. When air is removed, the collision of particles on the outside of the balloon are less frequent, and a lesser amount of pressure exerted on the outer surface of the balloon. Since the pressure on the outside of the balloon is now less than the pressure on the inside, the balloon expands. Now we're going to be dealing with gases in thermodynamics. We will always use absolute pressure. Avogadro's principle says something about the relationship between pressure, volume, and temperature, and the number of particles for gases that are made up of different types of molecules. The diagram below shows identical containers of H2, that would be hydrogen gas, 2 atomic mass units, N2, that would be nitrogen gas, 28 atomic mass units, O2, that would be oxygen gas, 32 atomic mass units, and water, which is of course a molecule made up of hydrogen and oxygen, 18 atomic mass units. These gases have equal pressure and temperature. What else is true about them? Avogadro hypothesized that equal volumes of gas will have equal moles of gas. So explain the relationship between the number of moles of gas, the number of molecules of gas, and Avogadro's number. Well, 1 mole of any gas is equal to Avogadro's number, which is 6.02 times 10 to the 23 amount of particles. The particles could be atoms, they could be molecules, or any small particle for that matter. Explain how to find the mass of a mole of gas and the mass of a single molecule of gas. The mass of any 1 mole is called the molar mass. To find the mass of a single particle, we divide the molar mass by Avogadro's number. Section 9.3, Quantitative Analysis of an Ideal Gas. This section consists of a long, complicated derivation of ideal gas law. To help you reason your way through the derivation, answer these questions. What basic law of physics does Edkina start with at the top of page 329? Newton's laws. Ideal gases are governed by Newton's laws. How does she determine the time between collisions? Answer with words, not math. She uses the impulse momentum theory equation. Look at the last 2 equations at the bottom of page 329. Answer with words, not math. What does Edkina turn into pressure? The pressure is the force exerted on by n particles divided by the wall area, the surface area of the wall, L squared. What does Edkina turn into volume? Volume came from L cubed, or the volume of the gas occupied. Now turn to page 330. Why does Edkina turn Vx squared into Vx squared plus Vy squared plus Vz squared? Well, this is because it is recognized that gas particles move in 3 dimensions, not just in 1. What does n times mv squared turn into? It turns into 3 PV, 3 times pressure times volume. The final statement is PV equals 2/3 N times K. Explain each symbol. P is the pressure, V is the volume, N is the number of particles, and K bar is the average kinetic energy of the particles. We are going to move past the thermal dice game, and we're going to find our way halfway through page 5, section 9.4, temperature. What does temperature really quantify? Temperature quantifies the kinetic energy of particles. Explain the difference between Kelvin and Celsius temperatures. If temperature increases by 1 degree Celsius, by how many degrees Kelvin does the temperature increase? The Kelvin scale for temperature is a way to have a 0 point as the lowest possible temperature. That is known as absolute zero. By definition, it is the temperature in which all objects cease to give off or emit any form of radiation. Now, all things emit radiation, and that's absorbed by other things in the environment. So absolute zero is really more of a hypothetical concept. But if something were to be lowered to a temperature such that it ceases to give off any radiation whatsoever, it has achieved what is called absolute zero, which is 0 Kelvin. Temperature in Kelvin is found by adding 273.15 to degrees temperature in Celsius. The temperature intervals on Kelvin are the same as Celsius, therefore changing the temperature by 1 degree Celsius increases the temperature by 1 Kelvin. State the ideal gas law using N and K and using N and R. Define all symbols. Well, these are our two different equations. We have P V equals N K T, and then we have P V equals N R T, where P is the pressure in pascals or newtons per square meter. V is the volume. Volume is always in cubic meters. Capital N, that's the number of particles, molecules, atoms, whatever. K is going to be referred to as Boltzmann's constant. We'll come back to Boltzmann's constant later. It's a value that's given on the table of information in your AP exam, so it's not something you need to memorize, but it is a constant. I guess we can define it now. Boltzmann constant is approximately 1.38 times 10 to the negative 23 joules per Kelvin. T is temperature. In Kelvin. N is the number of moles of gas. Which is basically a way of saying the amount of gas. R is the ideal gas constant. Which is about 8.31 joules per mole Kelvin. What is the relationship between temperature and average kinetic energy of particles? Well, temperature is an indication of the average random translation kinetic energy of particles in a gas. That's how we define it. What is thermal equilibrium? When two gases have the same average kinetic energy and therefore the same temperature, they are said to be in thermal equilibrium. Explain root mean squared speed of a molecule. State how this is determined. The root mean squared speed of a gas particle is an estimate of the average speed of those particles. Now, the average speed is slightly less than the root mean square speed, but it's a good estimate of that average speed. Let's move past this example here down to the very bottom, and let's calculate root mean square speed. If the air in the classroom is about 22 degrees Celsius, and I converted that from 72 degrees Fahrenheit, then what is the root mean square speed of a nitrogen gas molecule in the room? A molecule of nitrogen has a mass of 4.68 times 10 to the negative 26 kilograms. Well, here is my equation that I can use. the root mean square speed is the square root of 3 times Boltzmann's constant times the temperature in degrees Kelvin divided by the mass. So 3, Boltzmann's constant is 1.38 times 10 to the negative 23 joules per Kelvin, times, we need to turn temperature Celsius into Kelvin. So temperature is going to be 22 plus 273.15, and we get 295.15 Kelvin. All divided by the mass, which is 4.68 times 10 to the negative 26 kilograms. Pause the video and take a second to put that in your calculator. And it turns out that the root mean square speed, which is a decent estimate of the average speed of a molecule of nitrogen gas in a room that is at a temperature of around 22 degrees Celsius, is approximately 511 meters per second. Section 9.5, Testing Ideal Gas Law. What is an isothermal process? It's a process that occurs at a constant temperature. What is an isochoric process? This is a process that occurs at a constant volume, also known as isovolumetric. What is an isobaric process? This is a process that occurs at constant pressure. What relationship exists between pressure and volume? Well, an inverse relationship exists between pressure and volume. A direct relationship exists between pressure and temperature and volume and temperature. Test your understanding. Let's see how well we are working with the proportional reasoning involving these variables. Suppose you have two identical containers containing two gases with equal number of molecules. Container 1 holds hydrogen with 2 atomic mass units, and container 2 holds oxygen with 32 atomic mass units. Note that oxygen is 16 times more massive than hydrogen. Both gases are at the same temperature. Fill in the blanks in each sentence with a number. Use ideal gas law and other equations to justify your answer. The first one, the number of moles in container 1 is N. The number of moles in container 2 is well, it's also N. See, we have the same two containers containing two gases with equal number of molecules. If molecules are equal, moles are equal. So if the number of moles in container 1 is N, is 1N, then in container 2 it's also 1N. If the pressure in container 1 is P, then the pressure in container 2 is going to be 1p as well. You see, pressure is directly proportional to temperature. Both containers have the same temperature, therefore they should have the same pressure. If the average kinetic energy of the molecules in container 1 is K, then the average kinetic energy of the molecules in container 2 is also K. And this is because containers at the same temperature same average kinetic energy, because temperature is defined by the average kinetic energy. If the density of the gas in container 1 is rho, that symbol is rho, then the density of the gas in container 2 is, well, density is mass per unit volume. Density 2 is going to be 16 times the density of 1. Why is that? Because container 2 holds oxygen, which is twice as massive in the same volume. So twice as massive in the same volume. 32 is 16 times greater than 2. So, what does this tell us? 16 rho. If the root mean square speed of molecules in container 1 is V, the root mean squared molecules of container 2 is going to be, well, if the root mean square speed is equal to 3 times kT over m, that means the root mean square speed is proportional to the square root of temperature. Well, let's see. In container 1, the temperatures are the same. So although it's proportional to temperature, you can see root mean it's also proportional to the inverse of the mass. So I guess we could say for container 1, the root mean square speed is proportional to 1 over 1. We're going to consider container 1 to have a mass of 1 unit, and that's because container 2 has a mass unit of 16, because we can see that 32 is 16 times greater than 2 atomic mass units. Therefore, the relative mass is 16 times greater than that of hydrogen. Well, that's 1, and that's 1/4. So V2 is about 1/4 the speed of V1. Bigger molecules move slower. We're going to temporarily skip the dice distribution activity. Section 9.6, speed distribution of particles. Suppose you have a container filled with an ideal gas that is in equilibrium. Based upon pressure, volume, temperature, and the mass of molecules in the container, you determine the root mean square speed in the container to be 300 meters per second. Does this mean that all molecules are moving at 300 meters per second? Explain. No, the speed of the molecules are different and are on a distribution at that particular temperature. The root mean square speed measures, or is an approximate measure anyway, of the average speed of these gas molecules. The distribution of speed in a gas can be modeled using the distribution function f of v. What does the input v represent? Represents the speed of the particles of a gas. F of v represents the number of particles per unit. Therefore, if we were to take the number of particles per unit of speed and multiply it by the speed, what does the area give us? The area would be the overall number of particles. And we can see that by taking the area would be the number of particles per unit of speed times the speed, and you can see we end up with just the number of particles. For each section in the Test Your Understanding below, pause briefly to attempt each section, then resume to see if you are correct. Let's continue. Gases P and Q are in identical containers. Complete the following statements. Notice from the chart, gases P and Q have the same average speed at about 400, or the peak speed rather. The peak speed is at about 400 meters per second. If the number of moles of gas is P, the number of moles of gas for gas Q, well, let's break this down. N is the number of moles, little n is the number of moles, big N is the number of particles, and A is Avogadro's number, which is a constant. And what we know is the number of moles is the number of particles divided by Avogadro's number. Since Q has half the area, so if we were to go over to this right here and we were to kind of approximate the area to approximate the number of particles, you see how it makes a triangle here? Well, notice triangle under the curve that has Q has exactly half the height with the same base, therefore half of the area. Half the area means you have half the number of particles. Half the number of particles means Q has half the number of moles. That was a tricky one. The easiest way to figure that out, at least I think anyway, is to create little triangles here to help you estimate the areas in different portions. If the temperature of a gas is P, of gas P is T, the temperature of gas Q is, well, the curve shows a distribution at a particular temperature. So the temperature of P is the temperature of Q, therefore 1T. If the pressure of gas P is P, then the pressure of gas Q is, well, they have the same container, therefore they have the same volume. Since pressure is directly related to temperature, same temperature means same pressure. Therefore, the pressure at P is also the pressure at Q. If the average kinetic energy of particles of gas P is K, then the average kinetic energy of the particles at gas Q is, well, the average kinetic energy is equal to the temperature. If the temperature is the same for both, the average kinetic energy should be the same for both. If the density of a gas is rho, the density of gas Q is, well, density is mass per unit volume. We already determined that the number of moles is going to be half for gas Q than gas P, since there is half the number of molecules. However, here's what we know about how this relates to mass. You see, the mass of a gas particle is the molar mass divided by Avogadro's number. Since the number of moles of Q is half of that of P, then the mass of Q is going to be half of the total mass of P. If half of the mass in the same given volume, then you'd have half the density in gas Q. If the root mean square speed of P is V, then the root mean square speed of gas Q is, well, the root mean square speed, right, is proportional to the square root of the temperature. Since the temperature is the same, that part is the same, but it's also inversely proportional to the square root of the inverse of the mass. So root mean square speed is proportional to the inverse of 1 over the mass. Now, since Q, we already talked about it earlier, Q has half the mass of P, then when you take 1 divided by 1/2, you get the square root of 2. So the root mean square speed is, when we say it's proportional to the square root of 2, it means the speed of gas Q is about the square root of 2 times that of P. Last one, if the total internal energy of the gas is U, then the total internal energy of gas Q is, well, total internal energy can be related to U equals 3/2 nRT. The derivation is in the Kinetic textbook, which means the change in internal energy is 3/2 nR delta T. Okay, since the temperature was the same for both gases, okay, but the number of moles, so the temperature was the same, but the number of moles of Q was half that of P, then the internal energy of Q has to also be half that of P. Again, in the next test your understanding, please try and pause and see if you can do some of these yourself. Notice gas X has an average speed somewhere around double that of gas Y is about double the speed of gas X on average, the peak value. If the number of moles of gas X is N, the number of moles of gas Y is, well, again, you're going to take a look at approximating areas. So you'll notice that the height of both of these is about the same. And we can approximate it to about maybe right there. Okay, so we have a base of 10, okay, and a height of 1, 2, 3, 4, 5, 6, 7, 8. So 8 times 10 is 80, take half is around an area of 40. Now this other distribution curve would have an area approximated something like the same height of 8, but double the base from 10 to 20. 20 times 8 is 160. Take half of that, we get 80. So you can see the area of the distribution under gas Y is twice the area of under the distribution for gas X, which means we're going to have twice the number of particles. So twice the area, that means the number of molecules in gas Y is twice that of X. So if the particles are twice as much, then the moles should be twice as much. If the temperature of gas X is T, the temperature of gas Y is, well, the curve shows a distribution of a speed at a particular temperature, which means the temperature is the same for both. It is the speed that is a distribution and could be different at different points along the curve. The temperature is the same for all speeds along this curve. The pressure of the gas is P. The pressure of gas Y, well, it's the same container, same volume, pressure is proportional to temperature, so same temperature means same pressure. The average kinetic energy of gas is X, the average kinetic energy of gas Y. Well, if the temperatures are the same, the kinetic energies should be the same. If the density of gas X is rho, the density of gas Y is, well, what did we have? We had twice the area, therefore we had twice the number of molecules. We're going to end up with twice the moles. If we have twice the moles, we're going to end up with twice the molar mass, which means gas Y, if it has twice the particles, it's going to have twice the mass. Twice the mass means twice the density. If the root mean square speed of gas X is V, the root mean square speed of gas Y is, well, I mean, let's look at the gas. If the peak is at 800 for gas Y and 400 for gas X, then for gas Y it is approximately double. If the internal energy of gas X is U, the total internal energy of gas Y is, well, U depends on temperature. And since temperature is the same for both gases, you now need to look at the number of moles, because U is equal to 3/2 N R delta T. Since T is the same, the number of moles is what we're looking at. Since the number of moles for Y is twice as much as X, then the internal energy of Y is also twice as much as X. Okay, and for this final test your understanding, we have two distribution curves for A and B. Notice A is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9 units tall. B is 3 units tall. Curve A has a base of around 1, 2, 3, 4, 5 units. B has a base of about, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 units. So we're basically talking about the fact that curve A has a triangle that is 9 units tall, 5 units wide. 9 times 5, well, actually, I guess it would be in the hundreds. So each box is 100. So 500 times 9, and then take half of that, and we get about 2,250. Same thing as if we take the area under that, we have a base of, let's see, so 700, 800, 900, 1,000, 1, 2, 3. You have a base and then a height of 3 units. And we end up with the exact same area. Okay, so the exact same area means the same number of particles. So same number of particles, same number of moles. If the temperature of A is T, the temperature of B is, well, let's figure this out, okay? The temperatures are based on the root mean square speed, but the temperature of gas A is T. The average speeds, right, are a little bit different, okay? But remember, this was based for a particular temperature. So temperature should be the same for both. PV is proportional to T. Since V is constant container for both, and T is constant, then P is constant as well. If the average kinetic energy of particles of gas A is K, then the average kinetic energy of particles of gas B, well, you have to look at this. Kinetic energy is proportional to V squared, since the peak speed of B is at 600 and A is at 200. It's 3 times greater. So since the speed of B is 3 times greater than A, we would say 3 squared. The kinetic energy is 3 squared, or 9 times the kinetic energy of A. If the density of gas is A is rho, then the density of gas B is, well, the number of molecules is the same, the total of mass is the same, the density is going to be the same. The root mean square speed, well, that's going to be 3 times greater. You can see that because the peak here is at 600, the peak here is at 200. 600 is 3 times 200. And if the total internal energy of gas A is U, the total internal energy of gas B is, well, the temperatures are the same. And if the temperatures are the same and the number of moles are the same, because U, right, is equal to 3/2 nRT. So if the temperatures are the same, because it's the same distribution curve for both gases, it's just different speeds. Now, the number of moles was the same because the number of molecules is the same. That means the internal energy should be the same as well. And so for gas B, it would be 1U.